Okay, so now coming to the algorithms itself, RL algorithms. Okay, there are plenty of algorithms. Okay, baseline algorithms, as I may say here, for solving or for obtaining an efficient or optimal reinforcement learning agent. Okay, starting with these algorithms, there are many variations of these algorithms as well, right? So all in all, you will have plenty of algorithms to solve RL problems. Okay, however, this course being RL for control, we'll focus on select few algorithms, right, which are used very frequently in control applications. Okay, namely, we will be studying about DDPG. Okay, one of the most common RL algorithm for control applications. Okay, DDPG stands for Deep Deterministic Policy Gradient. Okay, it is an actor critique method, not a policy gradient method, by the way. Okay, and then you have TD3. I'll just list all the algorithms that we'll be studying now. TD3, which is twin deep deterministic policy gradient, a variation of DDPG. Okay, for more stable learning. You will see later why we do that. Then a third variation, or rather a second variation of DDPG is SAC, soft actor critique. Okay, that also starts with the base of DDPG, but it encourages exploration better. Cool? Okay, which is very important in robotics applications, right? And then another algorithm that we'll be studying is PPO. Okay, proximal policy optimization. Okay, these three methods, DDPG, TD3 and SAC, are off policy. PPO is on policy and it is policy gradient. It is not actor critique unlike the other three. Okay, but these four are something that you will come across quite often, and I'm sure now even when you're working for your projects, you might have come across these four algorithms quite often, right? Is not policy gradient, it's actor critique. Okay, I'll talk about that as well. Why that thing? Okay. So, why DDPG? Why DDPG? The answers are exactly as you have for deep reinforcement learning, right? Because you want continuous control, right? Both in terms of action and space, action and states, right? You want to work in real world, right? Plus DDPG is deterministic in the sense that even with a neural network, for every state it will deterministically sorry, it will deterministically give you one particular action for one particular state, right? Which is very useful in robotic applications. But at the same time, it is not so good while training, right? Why? Because when you take a given action in a given state, okay, say after a given number of episodes, or initially when you're starting, you might start with a given set of actions for a state, okay, and you will always end up taking those actions in that states, right? That way you will not explore enough, right? So that is one issue with DDPG. Okay, I'm telling all the issues as well earlier because we will be studying about how to counter them. Okay, so you have the goal is to, yes, directly optimize the policy. It was proposed in 2015. So DDPG was proposed in 2015, okay, and it has been popular ever since. So this roughly overlaps the time when reinforcement learning became deep reinforcement learning, okay. So this is one of the earliest deep reinforcement learning algorithms and still very effective, honestly. It's model free, obviously, because we are studying only model free algorithms now. Off policy because we can reuse samples, right? We'll see how it reuses samples. So in this, you have two neural networks, the actor neural, in fact, two sets of neural networks. You have two actor networks, two critique networks, okay, for stabilization of learning, okay. So the training, here you will see that the actor parameters are updated based on the gradient from the critique, right? So the critique is something that is to be optimized through the interactions, and based on that, because of the gradient, we will update the actor such that the critique, what does the critique do? Approximates the value function, right? So the updates happen to the critique such that the approximation of the value function is closer to the actual values, and in turn it will propagate that towards the actor to tune the policy such that you take the most likely action or the most optimal action in that state, right, which corresponds to the policy gradient part. Okay, so you see here that the update is happening both actor and critique, right? So the value function is being optimized, and because of that it propagates, and the policy is being optimized simultaneously, hence actor critique method. Okay, for stabilization, again the two tricks that we studied earlier will be implemented here, right? We use two neural networks, one an actor critique, the other the target actor critique, okay, to stabilize the learning, and then we even use experience replay, right? That is, we store these tuples in an experience buffer, reuse them or recall them in mini batches after given number of time steps to update the parameters of the actor and critique neural networks, right? The goal of the actor is to maximize the expected reward function, just as in any reinforcement learning, okay? But here you will see that it will include okay, mu theta, theta is basically the parameters of the actor network, right? Right? Okay. This is based on the deterministic policy gradient theorem, hence the name deep deterministic policy gradient, okay? Because we use this DPG, the deterministic policy gradient theorem, with deep learning, that is with neural networks. So when we fuse them together, we get deep deterministic policy gradient, okay? Hence the name policy gradient without it being policy gradient, okay? It comes under the class of actor critique, clear? Okay, so here what we are trying to do is find the, or rather using the gradient, okay, of the action value function to maximize that action value function's gradient so as to ensure that you reach the maximum value function while tuning the parameters of the actor such that you take the most optimal action in a given state, right? So you're tuning or optimizing both things here simultaneously, right? You're trying to get the most closest approximation of the Q values while also making sure that the policy parameters are tuned such that the actions that you take are the optimal actions, right? Or actions that give you the maximum return. Clear? Okay. And yes, here this is a very important thing that you have to keep in mind. The actor parameters are changed in the direction that increases the critique's estimate, or rather increases the accurateness of the critique's estimate, right? So implying the actor is heavily reliant on the critique's estimate of the value function. Okay, what is a value function? It's an expectation, right? So if the critique does not estimate the value functions correctly, the overall rewards that you're getting are incorrect, which would then mean if you update the actor parameters, that is the actions that you take based on an incorrect reward estimation, your action or your policy that you have will not be good, right? So here this is heavily reliant on the critique's estimate of an accurate value function, right? Because the actor parameters are updated through the critique's estimate, right? Not directly through the interaction with the environment, okay? As in policy gradient methods. In policy gradient methods, what do? You directly interact with the agent, sorry, with the environment through the agent, right? You see the rewards that you get, and you try to optimize the policy parameters or the probabilities of the actions by getting the feedback in terms of reward directly, right? Clear? The critique estimates the action value function or the Q function that we have, okay? Again, it's using exactly how we studied earlier, right? You have the Bellman expectation equation, right? So you have that, and you try to update the parameters such that you reduce the discrepancies between the actual value function and the estimated value function, right? For that, you have a loss function, which governs the update of the critique parameters. Critique parameters are nothing but the weights and biases of the critique neural network, right? So you see here your estimated value function and your actual value function. Say yt is your target value function or the actual reward that you'll be getting, and you simply have to reduce the mean squared error between that. Yes. Sorry again.
The loss
Uh-huh.
between the Q value
Uh-huh.
and the estimated the Q value and the
Okay.
this loss will be used for updating the actor and the critic. Or what? Or only
No, it will be used for updating the critique, and the gradient of this will be used for updating the actor. Okay, so the actor parameters will point in the direction that will increase the critiques, that will reduce the critiques loss, right? Okay. Yeah, so again here the critique, the actor updates its parameters based on the gradient of the critique. Clear? Okay. So what we are trying to do is how much actor parameters changes will change, increase or decrease the critiques evaluation, right? You see the sensitivity of that through this. So here both when the actor updates its parameters based on the gradient of the critique, okay, and say in the next episode the actor suggests a new action, and now when the RL agent executes that action in that environment, and based on that the critique will evaluate its entire estimation, right? So you will see by changing the action by that much, how much your Q value function will change. Yes. Yes. Okay, ground truth exactly like we studied earlier. It is a moving ground truth, right? You remember when we were talking about TD learning, okay? You had something called YT was your expected ground truth, right? But as you move forward, even both of them will keep changing. That's the reason why the learning is not stable. Otherwise, you could have the learning in one pass, right? However, because this YT is moving, Q will also move with it. Sorry again.
because in your report we have a ground truth, so we know the ground truth is always constant.
Exactly.
Here the ground truth change.
Yes.
Estimate.
Yes. Yes.
We cannot depend on the loss function.
No, we do depend on the loss function here. That's why the critique is updated based on the loss function.
But at first time steps, the loss function is not right.
It's high because you start with a certain estimated value function, which might be very far from the actual values.
Yes.
Okay. Yes, loss function will obviously go down. In any case, even in supervised learning, even when you have the actual targets,
In surprise, yes.
okay,
The ground truth is constant.
okay,
But here I don't know that the estimated value of the ground truth.
okay, okay,
I have an estimation for it.
okay,
At the first it must be wrong.
yes,
So I will give a random values for loss.
yes,
But at the end, the loss function will decrease.
yes,
But at the end.
yes, yes. Okay. you use target networks here. Okay? So your parameters, say your theta is the parameter of the actual non-target neural networks, theta and w, whereas theta dash and w dash are the parameters of the target, actor and critic. So they are updated less frequently, right? To stabilize learning, as we talked about earlier. And we have an experience buffer here, okay, which stores all these tuples, which will let you resample them in batches to update the actor and critique accordingly. Got it? Okay. Because this is inherently deterministic, right? The exploration is poor in DDPG, right? So we have to force exploration, and we do that through the induction of noise and actions, right? Say after the actor gives us a certain action, before executing it in the environment, we add some noise here at this point. Okay? And when we take that action, which is not the action that is ideal, because actor will give you an action for which it is the best one, right? It's not exploring anything. This noise will try to compensate for that, okay? Then it will give you a slightly different action now. So now you will end up in slightly different state. You will get a slightly different reward. And you do this multiple times, okay? So as to ensure that you have explored the environment fully, right? Clear? Here is a pictorial algorithm, I would say. So you will see you have an optimizer that will optimize the actor and critique neural networks. Okay, you see here that the critique is updated through the gradient from the critique. Sorry, the actor is updated through the critique's gradient, right? And when you take a sample, you store everything in an experience buffer. Okay, and then you keep resampling it to update your actor and critiques in mini batches. Clear? And when the actor takes an action, you add noise, okay, after the action, actor generates the action before it goes to the environment. And the reward or the feedback that you're getting is based on the action plus noise input, right? So this way you explore the environment, right? Yes.
By having noise, the reward from taking that action, like, oh, we think it will be referred to the action before having noise.
Yes.
Exactly. Because the problem,
No, that will not.
since it's not the wave action that gave us this reward.
Yes, okay, so I see your point. So you mean that the actor and critique think they are giving a certain action and they will try to update their parameters for that action, but the feedback they are getting is for a different action. No, that will not happen. That will not cause an effect, lot of effect, because the noise, first thing, is small. Okay, it's not that say your thrust is 5%, the noise induction will make it 55%. No, it will be from 5 to 5.5%. So that small change in a real world robotic system at least shouldn't make a lot of difference, right? So you're trying to learn it that way, that okay, fine, within this action range you will go to these states, right? Okay, yes. Okay, sorry again.
If I am in the action
Okay,
and I am updating the parameters C
okay.
okay, what I do with the actor network gradients itself? Do I use both of them of the gradient of critic and actor? Or
No, the change in actor critique will be through the gradient of the critique network.
and no use of the gradients of actor network?
That, what do you mean actor of the gradient of the actor?
In network I have gradients.
Yes,
Okay, but in actor network I depend on the gradients of critic.
yes, because how will you get the gradients in actor network? How do you get gradients in a neural network generally?
Back propagation,
And why does that backpropagation happen?
because I forget the loss and
Loss. There is no loss function for actor. That depends on the critique. That's why it depends on the gradient of the critique. Right? Yes, okay. Why DDPG works? Obviously because there is some sort of stabilization in it, okay, and because of the two neural networks that we use, plus because of the samples that we reused from the experience buffer that we have, that is the experience replay part, right? It is more stable, right? Clear? So because of all these things and being able to handle continuous actions and state spaces, we can use it for continuous applications. Hence, it is used efficiently, at least, right? For most applications. So yes, this again is a practical consideration that you need to take care of. Say when you are, if your values is too, change of the target network is too fast, you have to slow down the parameter that controls the update of the actor network, right? These are all practical considerations, by the way. Learning rate too high, you will have to obviously reduce the learning rate of either the actor or critic, whichever you think is learning too fast or too high. Insufficient noise, change the parameters. Okay, how do you know that there is insufficient noise? If you want, yes, if your acceleration is not good enough, right? And the activation functions itself might cause an issue, so you can change the activation functions depending on how you want your output to be, right? So that's that for DDPG. In the next class, we will study the different algorithm.